Have you ever been looking at a technical drawing or a piece of industrial equipment and seen that little code G6.3 and wondered, what on earth does that actually mean? Well, you're in the right place. Today, we're going to crack that code and figure out what this crucial standard is all about.
I mean, think about it for a second. You've got these huge factory rollers, massive pumps, spinning at unbelievable speeds. What is stopping them from just vibrating themselves into a million pieces? It's a really good question.
Well, the secret, it's all about balance, but not just any balance. It's a balance that's governed by a super precise international standard called ISO 1940-1. You can think of it as the rulebook that engineers follow to keep all that spinning machinery running smooth, safe, and sound.
So, to really get this, we need to understand its language. Let's start by decoding that G and the number that comes right after it.
Honestly, it's way simpler than it sounds. The G just stands for grade, and the number, in our case 6.3, is the absolute maximum speed of vibration that's allowed, measured in millimeters per second. So a G6.3 rating literally means that rotor cannot vibrate any faster than 6.3 millimeters every second. It's a hard limit.
Now, this little chart really helps put G6.3 in its place. You can see it's the standard grade. It's not for something that needs insane precision like a G0.4 grinding spindle, or the high-stakes world of a G1.0 high-speed turbine. Nope, G6.3 is the versatile, reliable workhorse for pretty much all general industrial machines.
Okay, so that's what the grade means. But how does an engineer actually know if a spinning part meets that G6.3 standard? Well, it all comes down to a little bit of math. And don't worry, it's pretty straightforward.
The entire goal here is to figure out and limit something called permissible residual unbalance. That's just a fancy way of saying how much uneven weight or wobble is this specific part allowed to have before it fails the test. That's the number we're trying to find.
And this is the magic formula they use to figure it out. This little equation is what translates that general G6.3 grade into a very specific, totally measurable, unbalanced limit for any part you can imagine.
And look, it looks a little intimidating, but it's really just three key pieces. First, you've got G, our balance grade, which is 6.3. Then you multiply that by M, which is just the weight of the part in kilograms. And finally, you divide the whole thing by omega, which is the part's maximum spinning speed. That's it. Those three things give you the exact unbalance limit for that specific rotor.
Okay, so the math is cool. It lets us get a real number. But theory is one thing. Where does this standard actually show up and make a difference? Let's take a look at G6.3 out in the real world.
The short answer is just about everywhere in industry. Seriously. We're talking about pump impellers pushing fluids, the fans and blowers that move air, flywheels and engines, crankshafts, drive shafts, even the giant rollers in paper mills and the guts of centrifuges and industrial mixers. G6.3 is truly the unsung hero that keeps our industrial world running reliably.
All right, now this part is super important. Before we finish up, there are three critical rules you have to remember when you're dealing with this standard. Getting these wrong can cause big problems.
Rule number 1. It is completely dependent on speed. Remember how that speed variable omega was on the bottom of our formula? That means the faster a part spins, the less physical weight unbalance it's allowed to have. Why? Because the shaking force actually gets worse with the square of the speed. So if you double the speed, you don't double the problem, you quadruple it. That's why faster parts need to be balanced so much more precisely.
Rule number 2, and this is a big one. This whole standard only applies to what engineers call rigid rotors. All that means is that the part has to be solid enough that it doesn't bend, flex, or change its shape when it's spinning at top speed. If it deforms, well, you're in a whole different ballgame, and you need a much more complex standard.
And finally, rule number 3, G6.3 is not a magic one-size-fits-all number. It's a target. To figure out the actual unbalance limit, which is usually measured in something like gram millimeters, you absolutely must know two things: the part's weight and its maximum speed. Without those two inputs, the term G6.3 is basically meaningless.
So you see, when you put it all together, G6.3 is so much more than just some code on a spec sheet. It's really the hidden engineering, this fundamental principle that lets all the powerful machinery around us run smoothly and reliably without tearing itself to shreds.
Kind of makes you look at the world a little differently, doesn't it? From the tires on your car to the tiny cooling fan whirring inside your computer, this whole idea of controlling vibration is absolutely everywhere. So now that you know the standard, what other hidden imbalances are spinning all around you?
Thanks for digging into this with me.